Hello, everyone. Um, Welcome back. I'm Professor Solomon today. I had a request, a couple, actually, a lot more than almost any other video I make, to continue the probability book solutions. So today will be chapter 2. Remember, this book is Probability Statistics and Random Processes, and this is 2.2 end of chapter problems. There's only 21 questions today. I have migrated to Word instead of Notepad. That way, I've done all the questions, solved all the questions in my notes. I will write out the easy ones, and then I'm going to just take snippets from my notes, and I'm going to paste them in Word. That way, we have a full answer for every problem, and I'll explain as I'm doing them. That way, if anyone has this for their homework or anything like that, you can just follow along. And yeah, let's get right into it. So question 1, I'm going to read the question first and then solve them just like last time. A coffee shop has 4 different types of coffee, and you can order your coffee in a small, medium, or large cup. You can also... Oh, my bad, I'm reading. You can also choose whether you want to add cream, sugar, or milk, or any combination of them. For example, you can choose to add all 3. How many different ways can you order your coffee? Super easy question. You take 4 times 3 times 2 times 2 times 2, which equals 96. That's the easy way. If your professor is a stickler for doing it, you can do it this way. By the way, you can use a star to do math, like multiplication as well as x. Depends on what you want. I usually use the star, by the way, because the x is usually a variable in programming, and it can get confused. But anyway, you can do one of these. 3 on top of 0. By the way, that's what that is. 1, 2, 2, 2, 2, 2, plus 3. Which gives you 4 times 3 times 8, which also equals 96. So that's if your professor is a stickler for stuff and wants it done the way the book wants it, not just using the easy multiplication principle instead of enumerating all the possibilities. Okay, question 2. 8 committee members are meeting in a room that has 12 chairs, and how many different ways can they seat themselves in those chairs? Okay, this is easy as well. We just have to use a factorial permutation. Now, if any of you know how to use the symbol for that, it's 12. So because there is 12 chairs, factorial over half of the empty chairs, because there's 8 people. So we take, there's 4 empty chairs, and then that's it. And that is, hold on, 11958 400. Do that with a calculator. Don't do that in your head. Okay. We have an A. We'll start doing it like this. An A and B problem. Let me check on my recording, make sure everything's still in view. Yep. Okay. There are 20 black cells and 30 white cell phones in a store. An employee takes 10 phones at random. Find the probability of that. Now, I'm reading these, just letting you know. English, once again, I have really bad dyslexia. I'm a math guy. So I'm going to read these the best I can, but you don't have to bear with me for reading. Okay, so for A, we're actually going to do this easier than how you're supposed to do it. This is how I'm going to do it. You're assuming, let me show you what they want you to do, assuming this is it. They want you to do this, equals bar, hold on, I actually don't know if that will stop my recording. I don't know if I can put the bar, but basically it's just like the absolute value of A over S. That's your answer basically, but we just have to fill that in. So if we're going to do it this way, we're going to go P4 equals 20. Now when I put a space here, that's 20 over 4. Over. Not on the side. Remember that. Then 30 over 6. Now on the bottom side, we're going to put 50 over 10, which equals 0.28 roughly. It's roughly that. It's a little off, but I'm sure if you get 0.28, you're probably right. If your professor is I would ask for the estimate 0.28 if I was giving this question. But if your professor is a little easier, they might just want the 20 over 4, 30 over 6, over 50 over 10 as the answer. But let me move that down here. That's A. And I hit Alt. My mistake. Okay. B. Once again, this is pretty much the same sort of deal here. Quite literally the same setup. So we're just going to take, this time it's B, like this. Now that B is underneath. So that B is underneath. And then it is less than 3. Okay. And it goes like this. And then it is 20, 0, 30, 0 over 50 over 10 plus 21, 30 over 9 over 50, 10. I wrote this out on the side. I'm copying it here. While I'm doing this, I want to make a little reminder that please subscribe. Only 1% of my audience subscribes, and that's really low. I would really appreciate if you would. I do make more content than just math and tutorial videos for programming. I make a lot of gaming stuff, and I stream live on Twitch for all my Let's Plays. So if you're into any of that, as well as you're a fan of programming math, just stay tuned. Everything might not be for you on my channel, but I am trying to grow all around. That's why I am the Dawn of Everything, not just the Dawn of Gaming or Dawn of Programming. I want to do a little bit of everything because I do like to do the gaming stuff to relax from my real job that I... and this, I just like math. I am a big fan. Anyway, once again, we're going to do an approximation, which is 0.14. Like before, this can be the answer right here, okay? If your professor is a stickler, like I am, you would want the approximation. As far as I know, the approximation that I would want as an answer is 0.14. Okay. Question 4. 5 cards are dealt from a shuffled deck. What is the probability that the deck hand contains exactly one and at least one ace? Okay. First, very easy. Once again, what we're going to do, 4, 1, 48 over 4 over 52 over 5, which equals 0.30. That's how I would do it. And that's all I would require for that answer. There we go. Now for B, very similar setup, but now since there is at least one ace, okay, we can consider that there's only one minus how many other ones there are. So 48 over 5 over 52 5, which equals 0.34. Once again, approximation here. I can't really do the squiggly lines on the keyboard, but just assume that all of these numbers that I'm putting equal to are probabilities. And since we're in probability, it's an approximation unless stated otherwise. Like these two are not, those two are exact. Okay, problem 5. 5 cards dealt from each shuffled deck. What is the probability that the deck hand contains two aces, given that we know at least one ace is... Okay. At least one ace. So this is a 2-part question, right? It's asking 2 different things. We have to do what we already know first. So we already know this. 48, 52 over 5 equals 0.04 approximation. Now, knowing this, we can use that in the NA is greater than or equal to 1, where NA is equal to 2. Since that's what this is, we can put 1 on top with our 0.04 with what we got above, which we know is 0.34 from the last answer, which gives us 0.12. That's our answer for this problem. Right here. If I was the professor, I would want the top part here for sure. Always show your work, because if you don't, then you can, professors can say that you're wrong just for not showing your work. Okay. The 52 cards in a shuffled deck are dealt equally among the players, column A, B, C, and D. Okay, easy enough. If A and B are exactly 7 spades, what is the probability of C being a spade? Okay. Once again, this is uber easy, but you have to think about it the right way. What we have to think about is we're looking at C4 here. Okay, and only C4. So when you have C over 4 like this, 20 over 9, and 26 over 13, which is all the cards probability, we can get 0.24 approximation. All right, 7. There are 50 students in a class. The professor chooses 15 at random. What is the probability that you and your friend Joe is among these students? Um, so there's 50 students, and you have to think about it this way. You and Joe count as 2, so you're looking at 48, and you can do it two ways here, depending on what you really. If you want to just use the amount and not use the opposite of A, and we're going to say A is the whole set. So I'm going to show you 2 ways here. You can do 49 over 14, like this, or 48 over 13, like so, equals 0.51. Now this is what I would want as the answer. Some professors would want this. 1 minus 48 over 15 over 50 over 15. It depends on who you ask. I would want this one, but if a professor wants this one, just put both on your paper, saying you can do it 2 different ways. Both of these are correct, but I always want the approximation. I believe most professors do, but if your professor doesn't, I understand. That's just not how I would do it. How many ways can you arrange the letters in the word Massachusetts? All right, this one's uber easy. Uber easy, okay? And don't overthink it. You take 13 factorial over 2 over and then 4 and then 2. Get your calculator out, which is 6, 4, 8, 6, 4, 8, 0, 0. That's how many, factorial. I'm calling it factorial, but it's also known as the permutation sign. Same thing. Anyway, so yeah. Number 9. You have a biased coin. So this coin automatically, we're going to rule out heads or tails being possible 50% of the time. You toss it 20 times. What is the probability that you have heads and 12 tails, and you observe 8 heads more than tails? Okay, so we know that the biased coin is automatically not 50-50. And this is one of those that I'm going to take a snip of what I did here. I'm going to do it like this. Now, let's go over this a little bit. This is B. I snipped the wrong one. Give me a second. A, B. Let me do A first, and then we'll get to that mess down there. A is easy. P is K8, since it's a biased coin. 20 over 8. P up. 1 minus P. Like this. Up 20 minus 8. All right, so that is the formula for binomial distribution. You should know what that is by going over the chapter, and that will tell you how you get 8 heads and 12 tails. Now, you can do it a different way, but I'm not going to show you the other way. I guess I can. You can just do P8 like this, and you still need 20 over 8 here. I'm just going to write it. It's basically the same thing. but it's a little cleaner depending on what you want. The way I'm looking over here is I just simplified it. I did that on my I did all these questions twice to make sure to figure out any other ways or to simplify some of my mistakes. But I did the second hand all by paper and pencil over there, because when you can't figure out something, always do it on paper and pencil. It seems to open your mind up on how to figure out something. Anyway, so let's get to this. You can use a summation to get this as well, but I try to avoid summations as much as possible because I hate the way calculus handles stuff. But basically, if both the number heads and then the other set of the tails are greater than 8, the observed heads or tails can be 9 or 11. 9 for heads, 11 for tails. If it's 10, then it's 10 and 10. And then if it's 11 heads, it's 9 tails. So those are events that are, what do you consider? Disjointed. They're disjointed events. And then you can just put them in this formula to prove that you can get 8 heads more than 8 tails. Because, to prove you get 8 heads more than 8 tails, because the coin itself is not 50-50. I hope that made sense. Best as I could say. Okay. A wire sensor grid consists of 21 by 11, 236. Okay. The sensor nodes located both imaginary numbers on a plane. I and J. Figure 2.1, the sensor node is located at 0.0. Needs to send a message to the node at 2010. The messages are sent to the destination going to each sensor. The neighboring sensor is located above or to the right. That is, we assume that each node is located at IJ. For sending the messages 0, 0 to 20. Okay. And then we have the lift here. Okay. Once again, don't think about this question too hard. It gives you the graph on the next page, but for a point of reference, every possible sequence must have a 10 or a 20, like a 10 US or a 20 RS. So you go 20 units up and 10 units up and 20 to the right, regardless of wherever you're going. So we can actually just do one of these. 30 factorial over 20 factorial over 10 factorial, which gives us 33045,015. And then you don't need anything else. That's your answer. Once again, math questions are all how you read them. They try to trick you, and just don't let it trick you, okay? They're meant to be there to be confusing. You have to really thoroughly read the problem to solve it. And to solve it right. Okay, in problem 10, we assume all the paths are equally likely, which is what was true. The sensor is located at 10.5, receives a message. That is the probability that is a random chosen path 0, 0 to 2010 goes through the point 10.5. Okay. Now, I'm going to show you two different ways to do this one. First, I thought it was as easy as this. This will count as an answer. I wrote this out first. This was my immediate response. 30 over 10. Now, this is the correct answer. I don't like it. If you gave this to me, I would give you partial credit because yes, it's the correct answer, but no, it's not what I think the question is asking. Okay? I would want this, and this is what the chapter is really all about. Two. Then you take all of that over 30. I'll fix this in a second. Okay. Now, we're going to take the bottom. Bottom's on the bottom. Okay. Like, all like this. This is the top. That's the bottom. And if you do it like that, you get 0.30. This is the real answer. This is what I would want. This is fine. It does count. I would count it, but I wouldn't give you all the points. If someone really wanted you to learn the subjects, the combination system in chapter 2, I would want it this way. Okay, 12. In problem 10, we assume that the sensor of choice is located. Okay. PR1, PA. Use the question in this. You want to use the questions here. This is how I did it. I actually had to check my work on this one with a colleague of mine. PA 10. Oh, like right there. Let me check if I'm still recording. Sometimes it crashes. No, I'm good. So that's how we as a together. This is lower, by the way, lower A, not PA. This is down, but I don't have a down arrow right now. So is this A, by the way. It should be lower by the P. If anyone knows of... That is the answer, okay? If anyone knows of a better way to do that, I'll be greatly open. But basically, A is denoting the event of 10-5. And then it occurs in the first 15 tries. There's 5 up and 10 right in any order. And then you get a binary outcome for the experiment. And you get 5 up, and you get a probability of PA, and then you can use binomial distribution to solve that. Okay, now 13. What is the probability of 3 heads? And then B. There's 2 coins in a bag. For 1 coin, pH is a half, and the other coin is 1/3. Choose your friends, toss it 5 times. Okay, these are the ones I'm going to snip because they take too long, and people complained last time that the way. So I'm going to snip them in, and then we'll talk about them. Okay. So that's A. And this is B here. Wait, no. This is how I did B here. Now, summations are terrible, okay? First, I'm going to read this. What is the probability of observing 3 heads? First, PI is the probability of flipping heads. Then, coin I is an element of 1 and 2, where Ci can be the event that I is chosen. Using the law of total probability and the binomial distribution, you can make what I did here. Now, once again, I did this one with a colleague of mine. He accepted this as the answer. He didn't go any further than this one. But I would, once again, always want the probability. I would not require you to do this top part right here if I was your professor. Or show this top part. You need to do it to figure it out, but show it. But I do need to know that you used NH is at least greater than or equal to 3. And then for B, you can use the fact where NH is greater than 3 has already been solved. We already know that it's 3.5, okay? And then you take PC2, which we already know is 0.5. We already know these two facts, okay? We already know C2 and 3. So all we need is the 21, the 0.21, which you can find out by the summation of 5 over J equals 3. You solve that out, you get an approximation of 0.21. Then you just do some simple math there, and you get 0.3. Once again, all I did there was just use Bayes' rule. If you can, Bayes' rule saves a lot of time and a lot of headache, actually. One interesting fact I wanted to bring up, the probability is less than 0.5, and we can tell that this makes sense since there's more heads that are observed than tails. And if one coin is chosen, the probability actually says that it lands heads is higher. So that's just a neat thing. All right. 14. There are 15 people in a party, including Hannah and Sarah. We divide the 15 people into 3 groups, where each group has 5 people. What is the probability that Hannah and Sarah are in the same group? Uber easy. We just go like this. Then we take the factorial, the setup like this. Remember, space means on top of. Then that's your top. I'm going to take bottom now. 3, like that. And then we have 15, 5, 5, 5 like this. And that will give you the probability of 0.29. We're on 14. Okay. 14. I was skipping ahead because I wanted to show some with 15. That's 14. Oh, I didn't put 15 here. My mistake. Aha. Okay. Now 15 can be done in 2 different ways, depending on how you want to do it. Let me read 14. You roll a die 5 times. What is the probability that at least one value is absorbed more than once? Okay. Now, it depends on what they want a decimal or actually want you to solve it. I will accept both of these on how I would do it. If you go like this, 3, 2, and then 6 over 5. And if you give me 0.91, I would accept that. Or if you're equal to 5 over 54, then I want you to, if you give me a fraction, I actually don't want you to do that. I want you to give me this. Hold on. I'm going to copy this here. You can do that, or you can do just this, right? And then subtract 5 over 54, which gives you 49 over 54. And 49 over 54 will also approximate to 0.91, I believe. Yeah, that sounds about right. I didn't actually do the calculations of 59 over 54, but I believe these two are the same here. I don't see why they wouldn't be, because you're just solving this. But yeah, if you want a fraction, this is how I want you to solve it. If they want a decimal and an approximation, do this. But the reason is, this is an approximation, by the way. If the reason is, if they want exact, you can actually give an exact. This is your exact here. If they want an approximation, this is your answer. In this case, since there is an exact like this, I would want this instead. But if you gave me 0.91, just in the circumstance, I would give you full credit for the answer. All right, so this is an A and B question. I have 10 red and 10 blue cards. I shuffle the cards, label the cards. If I write a number 1 on the first card and number 2 on the second card, what is the probability? All red cards are assigned numbers less than or equal to 15. And B is exactly 8 red cards are assigned numbers less than or equal to 15. Okay. Both of these are super easy. In fact, all they really are pretty close to just opposites of each other. So I'm going to do it like this. You go, well, we'll start with PA. I always use PA in the circumstances because I think that's important here, because with B, I'm going to show you how it's different. Also, if you've made it this far in the video, I just want to thank you for sticking with me. I know sometimes I can be hard to tolerate, but I really appreciate all of you in my audience, and I really hope these videos help you out. So that is A. There's a fly. There's a fly flying around. Anyway, so then we have like this is P. There we go. Like that. And then you want to do 10 over 7. 10 over 8. 15 factorial. 3 over 3. 2 over 2. 5 over 8. No. 5 factorial. 20 factorial. That sounds about right. And then that gives you 0.35 approximation. Both of these are approximation. And do you see the difference here? It should be apparently obvious. If A is the desired event, A, comma, is the event is the event that is almost identical to the first problem, where there's 15 factorial possible ways, since there's 15 cards, and there's a total number of permutations of 20 factorial. So I hope that makes sense to all of you. 17, I have 2 bags. Bag 1, 10 blue marbles. Bag 2, 15 blue marbles. I let you know right now, I hate marble problems when they use marbles. It never goes well. You have an ACT or SAT, and you're thinking of marbles. I hate just marbles. Hate marbles. Now 5 bags of marble without placing a random bag. If there's 2 red marbles and 5 chosen marbles, what is the probability I have chosen bag 1? Okay. Now, this is where I really start using the snip tool. Okay. Just to save on this here. And then I will I bet I better just write it out. I better write it out. Darn it, dude. Because I want it. This is a difficult question. Okay. Let's say BI is the event where I is an element of 1, 2. And NR is equal to 2 in the event that you choose 2 red marbles out of 5. You need to use Bayes' rule. Once again, this is Bayes' rule. So we're going to say that 6 over 2 and 10 over 3 is 16 over 5, which equals 0.41. That's approximation 1. Stick with me here. This is going to be confusing. Okay. While the probability of NR2 is conditioned, you got to choose bag. On choosing bag 2, you can say once again 6 over 2. Okay. 15 over 3. 21 over 5. 21 over 5 will give you 0.34. Now, you're not done. You have to put the relevant probabilities, okay, aka 0.41 and 0.34, into the Bayes formula. You should already know what the Bayes formula is. We've been using it, so if you know what you're doing, like this, then 0.5. Now, where did 0.5 come from, you may ask? Well, you have 2 red marbles out of 5 marbles. And you want to put that all over. That's the top of a fraction. This is the bottom of a fraction. 0.5 plus 0.34. There's our numbers again that we saved. And then we take the probability of 0.55. This is the answer I would want. I want you to show all 3 of these steps. If you show the full Bayes formula in letters, that's also acceptable. But definitely just show the numbers, of course. Okay, problem 18. In communications, packets are transmitted from the sender to a receiver. Each packet is received with no error, probability P independent from other brackets. The receivers decode a message as soon as it receives K, practiced with no error. Find the probability that the sender exactly receives. This one is the worst problem out of all of them. Out of all the problems here, I tell you, this was a pain. I doubt your professor would give you this as a problem. But let's go over this. EC here is the event that the error has not occurred. X is the trial. And we're going to seek all of the probabilities, okay? And then let's say the length is N. And the ending is EC, where, once again, the error has not occurred. The first N minus 1 entries can be any sequence. Okay, K minus 1 ECs, which denote by AN minus 1. All right. Then we find the probability we desire is PAN, the first part, AN, XN, EC, okay, by independence. We can say by independence, we can pull PAN minus 1 PXN equals EC. Okay. I hope I didn't lose you yet. But you want to make sure that PAN minus 1 is a binomial distribution. You don't make sure that it is. I'm telling you it is. And now this is your answer. This is look. This is one of those problems that if your professor gives you, he doesn't like you very much. It doesn't really help you learn as well, like the main contents of the chapter. I could see it as an extra credit, though. If someone gives this to you as an extra credit, I would give you that. But it's not a very nice thing to do, because I don't think this question really helps with what you're doing. It does reinforce skills you may have learned in a different class, though. All right, 19, sorry. How many distinct solutions does the following equation have? Uber easy. Uber easy. Okay? Now you can do this in two different ways. We're gonna do it one way, and then I'll do it another. Y1 plus Y2. Shouldn't capitalize them. Don't capitalize your Y's. That was because Word is weird and funky. Y5 equals 95. Okay. And then you have 5 plus 95 minus 1 on top of 95, which equals 95, like this. Oh, my apologies. I didn't mean to do that. It was supposed to be this. Anyway, this is an answer that could work. You could do it that way. You can also do it this way. 95 plus 5 minus 1, since 1 is always all of them. And then 5 minus 1, which gives you 99 over 4. I did it that way after thinking about it a while. Both are right in their own way. I don't think it really matters which one you give here, as long as you show how you got each one. I would personally go with this answer over this one. But I wouldn't say either of them are wrong. Just, I feel like this one's more complete. 20. Also, if he asks, both this, if you're wondering, is integer solutions. Okay? So if he's asking specifically for integer solutions, this is your answer. Okay, 20. Boy. This one's not as hard as you might think. How many distinct solutions does the following equation have? First, you go 0, 1 through 10. Then x1 is 0. Then the number of solutions for x1 is 1. Then the number of solutions, so on and so forth, okay? So it's 100 minus I, and you take the summation of 10, where I is 0, which is right here. Then you take your half, and then you get this. If you gave me just this and not actually solved it, I would understand. I would give you bonus points plus 2 bonus points if you gave me this, but if you gave me this, I would mark it as correct. So, yeah, I'm not going to go into this too much, but it's actually a relatively easy problem. If let's say you're a professor watching this video, and you give this to your students, I would say absolutely this does reinforce summations in a good way. It's not too hard, and it's easily solvable. 21. This is what you don't do. If you want your students to hate you, you can do this. Now, when I was in university, I actually solved this. See, I did this class probability as a because I wanted to go for math and computer science. So I solved this using a program a long time ago. And I actually went and dug it up, and I want to show you that in a second. But first, let me read this problem. Suppose that xi must be a non-negative integer, okay? And I is 1, 2, 3. How many distinct solutions does the equation larger than 40? Okay. So the top is the union of sets, right? Obviously. And you have to figure out how many are constrained to add to 100, basically. So going through, you can find the cardinality of A1, which lets you find Y1, which is equivalent to X1 minus 41. That gives you the elements for 1, 2, 3, so on and so forth. And you take that forward, and you can get 59 out of that. Okay, we have a number, 59. This is big. Now, 3 plus 59 minus 1 over 59 gives you 61 over 59 solutions. Which is right here, okay? The cardinality you can find by letting y1 be equal to x1 once again, and y2 be x2 minus 41, which is the same thing, which gives you y1, y2, and x3 being elements of 0, 2, and 3, all the way forward, okay? So eventually you'll get 18 out of that. Follow along. 3 plus 18 minus 1 over 18 equals 20 over 18 solutions, which is this. Then you can just put it in the simple formula and get 4, 9, 2, 0. Now, I actually saw a guy, I forget where it was. It could have been, what was it? GitHub. Make a Python problem for this, and then I decided to see if the Python worked, and it did. It ran it. So I'm not going to take credit for this, but if you want to solve it in a Python, maybe get some brownie points, this is how you do it. I don't know who, unfortunately it's been a long time, so I don't know who to credit this to, but I do want to say this Python code is not mine. But I do have it. I had it saved in my notes here. If you know who it is, then you know. I really appreciate for the help with this. But yeah, he's assigned I to the range 101, and J to the range 101, and K to the range 101. Okay, Tups is just a variable here with a function he's calling, and then he's calling the length. And he's making an equation out of it. These two are variables. If you know, I have a hard time explaining programming to someone who doesn't know it, but basically, if you know anything about Python, this is a super simple, super easy way to solve it. And it will also give you 4920 if you want to check your work. This is what I would do. I just did it this way. It shouldn't be so bad, but if you want to check your work, the computer in Python does do this. And if you are computer science / math, and your professor knows that you're doing both, this may get you brownie points, making a Python and showing it to him. Or extra credit. Let's say he has an extra credit. That may help. So that's the Chapter 2 problems. I want to thank all of you for watching. And if this gets enough likes and people start subscribing and asking, I got a lot of asks for this one. I will do Chapter 3. I really would like you guys to subscribe. Only 1% of people of my watchers subscribe. I would really appreciate it. I'm trying to grow here on YouTube. So I want to thank all of you for watching, and Professor Solomon is out. Have a good one, everyone.